Welcome to Ready to Derive. In this video, we will learn the ins and outs of slope-intercept form. For those of you who have never heard of that term, it's a way to write the equation of a line, a linear relationship, and it's of the form y equals mx plus b. If you haven't heard of that, that's okay, because we're going to start from first principles. We're going to introduce slope-intercept form using a real-life context to show why it makes sense to use this form. We're actually going to derive the form from first principles, and then we're going to do lots of practice related to finding equations of lines. So without further ado, let's get started. So let's begin with a scenario that lends itself to slope-intercept form. Many sort of scenarios will lend themselves to certain forms of equations of lines, and here's one that begs to be written in slope-intercept form. So you have $5 in your piggy bank, and you receive $2 for every chore that you do. So let's start to kind of find different ways to look at this. So one way would be to create a table. Okay, so let's have a look at how the number of chores affects the dollars you'd receive. So if you do no chores, you'll be stuck with $5. If you do one chore, you'll get $2 extra, 7, and 2 chores, that will be 9. You can see the pattern developing, and you can see that it's a straight line because you can see that the rate of change of y is constant. All right, let's have a look now at this in a graph. So here we go, instead of axes, and if I just, let's see, just roughly scale the x-axis, okay, and maybe this is the y-axis. So we see that, let me just change the color up. So when we do no chores, we have $5, that's this one here. One chore, $7, 2 chores, 9, so it's just approximate 3, 11, 4, 13. And we can see that indeed it does create a straight line. Now, so table, graph, and the other most important way of describing a relationship is making an equation. So let's sort of see what equation, how we could generate this equation. And it's helpful to look back at the table and just kind of envision what would happen, say, if we did 10 chores. Would there be a way to predict how much money we'd have after 10 chores? Well, if you notice, let's have a look at this. For every 1 increase in chore, your piggy bank account goes up by $2. So $2 each time, and depending on how many chores you do. So if you do 10 chores, that means that you're going to start with your $5 that you had, and you're going to add $2 10 times. So we write 2 times 10. I'm not even going to put the answer because it's more interesting to look at the structure. And by this reasoning, if you do X chores, well, whatever X is, you start with $5 and you add to that $2 times the number of chores, because that would be the number of jumps you'd have to make down this table. So that lends itself, so the equation, now we're going to use this, remember this is X and this is Y, so the equation becomes Y equals 5 plus 2X, which should look like slope-intercept form to you. You might be more used to seeing the X term come first. And so you have y equals 2x plus 5. And if we think about what these represent, so the 5 we see is actually the y-intercept, right? That's the amount we have in the in our piggy bank before doing any chores. And the 2, and you might not have seen this, but this is indeed the slope. You might not have noticed. You probably noticed it in the table. Notice that every time we go up 1 in x, y goes up 2 by 2. And if we look, let's have a look at the graph. The same thing happens. You go over 1 chore. That results in an increase of $2. I should have put dollars on the y-axis, number of chores on the x. So every increase in 1 chore, you go up $2 in your piggy bank account. Now, one other thing, notice that I don't have any, I'm not connecting these dots with a line. The reason is if I put a point there, that point would be suggesting that I did like maybe 3.5 chores Well, there's no credit, I think, given for partial chores. So 3.5 chores or 3.9 chores doesn't really apply, which is why I'm not connecting those points with a line, no matter how tempted I am. So here we have the general equation of a line in slope-intercept form. Notice that slope is the m value that gets multiplied by x, and the y-intercept is the b. So in this slide, we're going to actually derive slope-intercept form from first principles, just using the slope formula. So let's get our axes, let's get a line shown there, and let's bring up the slope formula. So the slope of a line is y2 minus y1 over x2 minus x1. Wherever we choose those points, that slope has to remain the same. So I'm going to pick our favorite point, which is the y-intercept here. And we're going to think about what's special about the y-intercept. Well, we know that we generally use b for the y value, but what is the x value at that point? Well, if you're on the y-axis, your x-coordinate is, any point along the y-axis is going to have an x-coordinate of 0. So we've got that. Now for slope, though, we need a second point. So I'm going to pick some random point up here, and I'm just going to call it x, y. Not x2, y2, because I don't want to use specific numbers, but I just want to keep it general. Otherwise, I won't get an equation relating x and y. And now I have to, so the slope between those 2 points, so let's think about it. If I move this point up or down, no matter how close or how far from the y-intercept, the slope must remain the same. So let's use those general points and plug into the slope formula. For simplicity, I'm going to call this point x1, y1, and this x2, y2. So we have m equals, so y2, we're just going to keep generic y, minus y1 is our b value, over our x2, which is just x, and x1 is 0. And if we simplify this, x minus 0 is just x. If we put m over 1, we can maybe see that we could cross multiply and write this as mx equals y minus b. And then hopefully you're seeing that if we add b to both sides, voila, we get slope-intercept form. So y equals mx plus b. And what I'd like you to, one more thing to notice is that we know that slope is rise over run. So if we have a slope of m, it means if we run over 1, we rise by m. That also would mean that if we went over 2, that means we'd rise up 2m. Has to stay proportional. So it makes sense that if we run over between the 2 points, it's a distance of x. If we run over, our run is x, then our rise should just be, to keep things in proportion, just be m times x. And hopefully now that makes sense that if the y-coordinate of this point here is b, and we're interested in the y-coordinate of, the point x comma y, that y-coordinate, well, all we have to do is take b and add the distance mx to it, so that our new y-coordinate will just be b plus mx, or y equals mx plus b. So for our first practice problem, we are going to practice graphing equations of lines in slope-intercept form. So here's an equation of a line. It is in slope-intercept form. We would just have to rearrange it, but it's of the form mx plus b. And we're going to learn a shortcut for graphing. So you could always make an xy table and plot the points. So for example, or not even a table, just come up with points. So you could say, well, when x is 0, what's y? 3 minus 0 is 3. Oh, look, that's the y-intercept. That's actually going to be very useful in a moment. When x is 1, 3 minus 1 is 2. So we already have 2 points. If we continued like that, we could easily graph the line. But that can be a bit tedious at times, and instead we're going to be creative and use the slope and y-intercept to make a quick sketch. So first of all, let's rewrite this as negative 1x plus 3. So it's in the form we're accustomed to. So the y-intercept, the plus 3, that's the y-intercept, and the slope is negative 1. So let's pull up a graph and plot the y-intercept, which is at 3. So I have my first point, 0, 3. And now, but let's think, how are we going to use the slope of -1? What are the instructions embedded in the slope of -1? Well, if you think that it's really -1/1, then you can, and you know it's rise over run, then the -1 in the numerator means down 1, and the positive 1 in the denominator means right 1. So let's work from the y-intercept, and let's go, let's see, down 1, right 1, and that puts us a point there, and we can continue that pattern. So the dotted line is just to help you see the rise and the run, but it's not actually part of the line, so I'm going to continue that there. We could also reverse that process. So if you chose to actually go up 1, then you would go left 1 in exchange. And so from the y-intercept again, we could go up 1, left 1, and continue in that way. And then now in this case, we do connect the dots because x could be a half, right? 3 minus a half would be 2.5. So that's allowed. So we will connect the dots, and this is the graph of the line. So for the next one, here we have it. This is in the form we already need. The y-intercept, let me just use white again. So the y-intercept is -4. The slope is 2/3. That means up 2 and right 3 because they're both positive. So let's start at the y-intercept of -4, and we will go up 2 and right 3, up 2 and right 3. And we can also acknowledge that this, we could have written -2 over -3. That's still a positive slope in total. What that would mean though is down 2, left 3. Let's see if that works. So come from the y-intercept, go down to left 3. Yes, that works. And there we will connect them, and we've successfully graphed slope-intercept form using a shortcut rather than making a table of values. So in this practice problem, we're going to reverse the process from the slide before, and we are going to practice writing equations of lines in slope-intercept form given a graph. So here's a graph of a line, and clearly the first thing we have to do is identify the y-intercept and the slope. So the y-intercepts, hopefully, as long as the y-intercept is a nice number, which they are for these problems, so the y-intercept seems to be 4. Now the slope, it's important to pick good points to find the slope. So it's no good, don't think about, oh, go over 1 and go down tiny fraction. That's really going to be hard to accurately guess. So go to the next available point that lies at the intersection of the grids, and we can see, does that look about right? Yes, it does look right, that the slope, if we go from this point, from the y-intercept, we go down 1 and we go right 3. We could also go up 1 and left 3. It's the same thing. The slope is going to be -1/3. And that means that the equation of the line in slope-intercept form is y equals -1/3 x plus 4. Let's practice this again. So in this case now, interesting, what is the y-intercept? Sometimes people say there's no y-intercept. Well, that's not true. The y-intercept is in fact 0. So that is important. We need to take that into account. And the slope. So the slope, let me just get rid of this here now. So the slope we want to pick, let's see, well, we know this is a point here, and the next nice point seems to be right here. And the next nice point, when I say nice, it means the coordinates are integers. So we have here, we go to the right 2 and then up 3, and we could have gone left 2, down 3. They both work. So on either way, the slope is going to be positive 3 over 2. And the equation of the line is y equals 3/2 x plus 0, but there's no need to write the plus 0 with it's implied. Continuing the same practice, here's a line, this horizontal line. Let's see if we can write an equation for this. So it seems like the y-intercept is 2. And what is the slope? Well, if you pick any 2 points on this line and think about the rise and the run is 3, but the rise is 0. and 0 over 3 is just 0. So it doesn't matter which 2 points you pick, the slope of a horizontal line is always 0, so we can write it as y equals 0x plus 2, but it seems like we're writing more than we need to, so often it's just written as y equals 2. And that's the equation of any horizontal line, is going to be of the form y equals some number. And here we go, vertical line. Now what is the y-intercept? Oh, let's see, the y-intercept, there is no y-intercept, right? Undefined, doesn't exist. What is the slope? Well, in the same reasoning, you can think, well, if I connect 2 points, if I think about the rise between those 2 points is 3, but the run is 0, and 3 divided by 0 is undefined. So I cannot write that in slope-intercept form. In fact, you do need to know how to write the equation of a vertical line. That's going to be of the form x equals 2 instead of the horizontal line was y equals 2. So this sort of makes sense. Another way to think about it is that if you find the x-coordinate of any point along this line, wherever you are, is always going to be, the x-coordinate is going to be 2. It doesn't matter where you are. If you're up here, it would be 2, 3. So the only thing you can say for sure is that x is always 2 along that line. So for a third practice problem, we are going to practice writing equations of lines in slope-intercept form given 2 points. So here are the coordinates of 2 points, and in order to write slope-intercept form, we've got to first find the slope. So let's make this x1, y1, this point, and x2, y2. It doesn't matter which is which, as long as you're consistent. So we would get -3 minus 5 over 6 minus 2, -8 over 4, which is -2. So in the equation y equals mx plus b, we do know now that we can substitute m as -2. The problem is we don't know what the y-intercept is. Notice that because the x-coordinate of neither of these 2 points is 0, we can't use those y-coordinates. Those are not the y-intercepts. Now, this can be done algebraically, but let's go geometrically first to see if we could sort of estimate the y-intercept. And first of all, if we acknowledge that the slope is -2 over 1 or 2 over -1, we can use those to our advantage by let's work with the point 2, 5, since that's closest to the y-axis. So 2 up 2 left 1 would put us there. Up 2 left 1 shows us that the y-intercept is indeed 9. It works out nicely. So we could say that the equation of this line, we are pretty sure it's this. But what if the y-intercept was not a nice number like 9? Well, in that case, we need an algebraic method. And this is where we would plug in one of the points into the equation and solve for b. And it doesn't matter which one. They both will give the same answer as for b, because they're on the same line with slope -2. So let's plug in the point 2, 5 for convenience. So y is 5 and x is 2. And if we solve this, we find that b is indeed 9, which proves that what we had already inferred from the graph, but without having to use a graph. And just for demonstration purposes, let's just prove that this would work if we had used 6, -3 instead. So we would get this, we get -3 equals -12 plus b, and yes, indeed, b would come out to be 9. So in the next slide, we're going to formalize this and do one more practice problem. So let's begin with an example to lay out the steps for this very important skill of being able to write equations of lines in slope-intercept form. So step 1, as we know, is to find the slope of the line. And so if we use the slope formula, let's bypass writing the formula out and just go straight to subtract the y-coordinates over subtract the x-coordinates. We get -8 over 10, which simplifies to -4/5. And step 2, as we saw before, is to plug in the coordinates of one point and solve for b. Well, let's put in the -4/5 for the slope first, and then let's plug in one of the points, say -2, 7. So we get 7 equals negative 4/5 times negative 2 plus b. So 7 equals negative 4/5 times negative 2 over 1, if you think about it, it's easier to think about it like that, is 8/5 plus b. Now 7, since we're going to be dealing with fractions here, we want to rewrite 7 as how many fifths is that? So 7 would be 35 fifths, and then we can just subtract 8/5 from 35 fifths and get 27 fifths for this y-intercept. Now the last step seems sort of simple, but people often forget to do this, is to write that we have to rewrite the final equation with y expressed in terms of x. So sometimes people just feel like they solved for b and that took so much work that they're done, but let's not forget to go back to the original equation. So y equals negative 4/5 x plus 27 fifths, and there we have the final equation of the line in slope-intercept form. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.